For bell work today, give it an angle in quadrant 2 and with a measure of sine of that angle being 1/3, tell me what the cosine of that angle would be. Oh, I forgot to hit the timer. Keep accidentally clicking the screen. Okay, let's go over it. So it helps if you draw a picture of it. This is quadrant 1, 2, 3, and 4. Our angle in quadrant 2 will be right here, about. And if we connect that angle to the right, to the x-axis, it makes a right triangle. Okay, and so if you have a right triangle, we can then use our formulas, which you should have from 4.4, but to be honest, if you use your formulas for the unit circle, that you'll get the right answer eventually. But the side of our angle, if you use 4.4's formulas, is y over r. So since our sine value is 1/3, that means y is 1 and r is 3. If we want to find cosine, the cosine formula you should have is x over r. So the only thing I need to do to find this answer is really to find our x value. So if you label this using our values over here, y is 1 and r is 3, we can find the x value with the Pythagorean theorem. A squared plus b squared equals c squared. Or 1 squared plus x squared is 3 squared. One times 1 is 1. 3 times 3 is 9. Which means x squared has to equal 8. To get rid of this squared, we square root both sides, so x is the square root of 8. You could simplify that though, because 8 is the same thing as 4 times 2. And 4 is a perfect square. The square root of 4 is just 2. Okay, I will tell you, this answer is actually wrong right now. There's something we're forgetting or missing. Does anyone know what it is? What's wrong about this answer? It should be negative because we're left of the y-axis, right? This is where you have your negative x values. So this should be negative 2 square roots of 2. And so if we plug in our x and r values now, the cosine would be negative 2 square roots of 2 over 3. Okay, any questions over the bell work? Okay, we're going to do today then 4.6, which is a easier lesson than 4.5. If you are up to date with 4.5, we're basically just extending those principles of what the A, B, C, and D values do to our graphs, and we're applying that to the other trig functions. If you aren't there yet, that's okay. Today will be more review, hopefully, to get you so that you're have a good understanding of 4.5's material. Again, so for today, we're going to do these. We're going to sketch graphs of tangent, cotangent, secant, and cosecant functions. And actually, I went ahead and cut D. I don't think we had enough time to go over it in my other hours. So, and to be honest, it's not used that much at all. If you want to learn about damped trigonometric functions, you can. It's in the slide, it's in the lecture notes, it's in the textbook, but I'm not going to test you over it. All right, so first things first, how do we graph tangent functions? Well, to graph a tangent function, remember that the tangent of any angle is equal to y over x. So to get the key values that we'll use for tangent functions, we're going to look at basically two things. What happens when the denominator is negative or 0? I'm sorry, what happens when the denominator is 0? And what happens when the numerator is 0? The denominator is 0 on a unit circle whenever the x value is 0, which would happen at 90 degrees when your point is 1, 0, and negative 90 degrees at negative 1, or 0, negative 1, and 0, 1, right? On the y-axis at 90 degrees and negative 90, which is the same as pi over 2 radians and negative pi over 2. And when that x value is 0 at those points, what happens is any number divided by 0 is undefined, right? You can't divide by 0. So those make vertical asymptotes in our graph every pi over 2. And as you get closer to those values of pi over 2, you'll see that as we get closer to negative pi over 2, our y values go infinitely in the negative direction. And as we get closer to pi over 2, our y values get infinitely larger. If we look when the numerator is 0, the numerator is 0 at 0 degrees and 180 degrees. Right? Whenever your angle is on the x-axis, you have a y value of 0. So that'll happen every pi units. And 0 divided by anything is just 0. So every pi units, we get an x-intercept of 0. So because of those two facts, what ends up happening is the period of our tangent function is just 1 pi instead of 2 pi. It only takes 1 pi to get from one asymptote to another and for our graph to repeat. Our asymptotes then happen every pi over 2 plus n pi. So 1 pi over 2, 3 pi over 2, 5 pi over 2, and negative 1 pi over 2, negative 3 pi over 2, negative 5 pi over 2. You should also note that tangent is an odd function. It is symmetric about the origin. If you rotate it 180 degrees about the origin, it'll land on top of itself. So that gives us 3 key points we can use to graph an asymptote, an intercept, and an asymptote. Ideally, we would like 5. And so for the other 2, what we're going to use is this negative pi over 4 value and this positive pi over 4 value. Because those have a nice y value to go with them. At negative pi over 4, y and x are the same value, so you get negative 1. And at positive pi over 4, y and x are the same value on a unit circle, so you get positive 1. So basically, our order is going to be, our pattern is going to be asymptote, negative 1, 0, 1, asymptote. Asymptote, negative 1, 0, 1, asymptote. And so to graph these by hand, you will do the exact same thing you were doing for sine and cosine. You'll identify what your A, B, C, and D values do. And then you're just applying that to a different pattern. Instead of going from 0 to 2 pi, we go from negative pi over 2 to pi over 2. And instead of going intercept max, intercept min, intercept, we do asymptote, negative 0, 1, asymptote. All right, so is there any questions about this, or does anyone need more time to write before we look at an example? Okay, let's do it. So for example, let's say we have the graph y equals negative 3 tangent of 2x. So to graph this again, we start out just like we did for sine and cosine. Our A value here is negative 3. That tells us 2 things about the graph. One is that we're going to multiply our y values by 3. And to be honest, that's not going to have as big of an effect as it did for sine and cosine, because an asymptote times 3 is still an asymptote. 0 times 3 is still 0. So the only numbers that really change is negative 1 becomes negative 3, and positive 1 becomes 3. The second thing our value tells us is because it's negative, that means we're going to reflect our graph over the x-axis. But again, that's actually not going to have as big of impact as it did for sine and cosine, because an asymptote flipped over the x-axis is still an asymptote. 0 flipped over the x-axis is still 0. So all that really happens is that negative 3 and 3 are going to switch in the order. So instead of going 0, negative 1, 0, 1, 0, asymptote, negative 1, 0, 1, asymptote, we'll do asymptote, positive 0, negative asymptote. Our B value is 2. And our B value tells us about the period of a function. So the period of our function was pi. And so if we divide that by our B value to get our new period, it would become pi over 2. Or another way to think about that is, since our x values are now going twice as fast, it takes us half as long to get through a cycle. We could get through a cycle in half the normal time since we're now going twice as fast. All right, so if I use this to graph my function, oh gosh, let's try that again. All right, normally I would start at negative pi over 2, but since the period has been halved, I'm actually going to start at negative pi over 4. Or usually how I'll actually do these is I'll start at the origin knowing that that's going to be my midpoint, and I'll go half the period to the left and half the period to the right. And a good way to double check is you should note that the length then from your cycle should match up. From negative pi over 4 to pi over 4 is a length of pi over 2. Its halfway point is the y-axis. Its quarter point would be negative pi over 8. And its 3/4 point would be pi over 8. All right, and then again, it goes asymptote. It would normally then be -1 next, but instead, we're going to do +3. Again, it's been multiplied by 3 and reflected over the x-axis. 0. We would normally do 1 next, but again, it's been multiplied by 3. It flipped over the x-axis. And then asymptote. So we get a graph that looks like this. Okay, if at this point of the class you're like, oh no, you have lost me, Mr. Lake. I do not know what you're talking about. I don't know if I'm going to be able to do everything that you just showed. Remember, this is how to do this by hand. It would be great if you knew how to do these by hand. But ultimately, if you could graph these at a calculator and then use your calculator to pull out any of this information that you would need, that is fine. So if I graph this in Desmos as -3 tangent of 2x, I could use that to find my intercepts and to check my graph. So yes, this has an intercept of 0, 0, and so did mine. What will be a little bit of a pain is it's not as easy to check the rest of your points, right? If I try to click pi over 8, 3, that's not a point that they have graphed here. I can fix that really easily by just graphing the line y equals 3. And then I can see that that really is the point -pi over 8, 3 on my graph. Similarly, you will see that it doesn't graph the vertical asymptotes at all. But if you graph x equals, what do we say, -pi over 4, then you can check and make sure that, yeah, your graph actually never does cross that line. So that is a vertical asymptote, or a vertical asymptote. All right, so is there any questions about this? All right, then it's your turn. Graph y equals 2 tangent of x over 2. I'll give you 2 minutes. And again, if you've been working on this by the end of this, like a minute 30, minute 45, and you're like, I don't know what I'm doing when I'm doing this by hand. Try graphing it in a calculator. That way, at least you do have a graph of it. And then we'll talk through again how to do it by hand. All right, your graphs both look like they're supposed to look. They don't have any labels on it or anything, so I don't know if they're going through the right points, but it's how they're supposed to look. All right, let's go over it. So our A value is 2. And again, that tells me 2 things. It tells me that my value of -1 is now going to be -2. And my value of +1 is now going to be 2. And because it's positive, I am not reflecting over the x-axis. Our B value is 1/2. So that tells me that if I take the period of pi divided by 1/2, I get a new period of 2 pi. Whenever you divide by a fraction, remember, you flip and multiply. So if I start at the y-axis, I'm going to go half the period to the left, so -pi to the left, and half to the right. So pi to the right. And again, if you double check, the length from -pi, -1 pi to +1 pi is 2 pi. The halfway point would be the y-axis. Quarter way point would be -pi over 2. 3/4 point would be +pi over 2. Our pattern then is to do asymptote. -1, which has now been multiplied to become -2. 0, +1, which again has been changed to 2 by our A value, and asymptote. So you get a function that looks like, oh gosh, that's terrible. That's terrible. Like that. Yay. All right, any questions about this? Okay, The rest of this class will be really easy then. Because if you know how to do sine, cosine, and tangents, you can get all the rest of the graphs because they're all just reciprocals of your graphs. So for cotangent, and I'll be honest, if you just want to include this graph and not all the properties, that's okay. If you also just did the graph and not the properties for tangent, that's okay. Because the back of your book has all your parent functions. So if you ever needed any of this information, it's in a nice little reference chart in the back of your book. All right, so to graph cotangent, the cotangent, remember, of any angle is just x over y. It's just the reciprocal of tangent. And so functionally, again, if we look at the zeros, you'll see what happens to this graph. Our y value is 0 on the x-axis. So at 0 degrees and 180. So now it has a 0 in the denominator every n pi, like 0 pi, 1 pi, 2 pi, 3 pi, negative 1 pi, negative 2 pi, negative 3 pi. And the numerator will be 0 whenever x is 0, which happens on the y-axis at pi over 2 and negative pi over 2. So then our x-intercepts are now pi over 2 plus n pi. So 1 pi over 2, 3 pi over 2, 5 pi over 2, and negative 1 pi over 2. All that happened was these switched. That's all that happens between a tangent and a cotangent. So functionally, what that does is two things. It reflects your tangent curve over the x-axis, and it shifts it to the left or right, to be honest, by pi over 2. So if you look, this is the same as our tangent curve, but flipped over the x-axis and shifted to the right, pi over 2, or to the left, pi over 2. So its pattern that you will use is very similar. It'll be asymptote, +1, 0, -1 asymptote, like we did for that example. So it'll be asymptote, +1, -0, -1 asymptote. And instead of going from negative pi over 2 to pi over 2, it'll go from 0 to pi. So the halfway point would be pi over 2. The quarter way point would be pi over 4. And the 3/4 way point would be 3 pi over 4. All of its properties are very similar then to a tangent. It has a range of negative infinity to infinity. Its period is also 1 pi, and it is an odd function. If you reflect this, rotate it around the origin 180 degrees, it'll land on top of itself. Okay, so rather than do another example like this, I do have one in the lecture notes and in this slide. So if you want, you can do this problem and then check it against the lecture notes. I think if you also look in the textbook, they have more examples. And also if you go to WebAssign and watch the videos, they have examples over this. But I think it might be a little bit redundant at this point. So unless everyone has any questions or need more time to write, I think we'll move on to cosecant and secant. That way I get time to show you an example of one of those. All righty then. Okay, so for cosecant and secant, these are actually really easy to graph. If you know how to do 4.5, you can graph these in the same amount of time that it took to do any of those problems, plus about 5 to 15 seconds. Remember, cosecant is the reciprocal of sine. So to graph cosecant functions, all we are going to do is to graph the sine function first. And then whenever you have a minimum or a maximum on the sine function, it will touch the cosecant function. And whenever you have an intercept on the sine function, that's an asymptote for your cosecant function. Because cosecant is just the reciprocal of sine. So if you think I have 1 and I flip it over, 1 over 1 is still 1. If I'm at -1 and I flip it over a fraction, 1 over -1 is still -1. But if you're at 0 and you flip that over, that becomes 1 over 0, and you can't divide by 0, so that becomes an asymptote. So basically, all of your maximum and minimums are where your graphs will touch, and you'll make U's at that point. And every intercept is where you will have a vertical asymptote. That exact same pattern holds for cosine and secant. Same thing. They touch at the max and min points, and they have asymptotes at the intercepts. So as a result of these, a lot of these properties, which again are just in the back of the book, you don't have to rewrite all these, are the same or can be derived from sine. So the domain is all the numbers except the x-intercepts of sine, which are all the pi and pi values. 1 pi, 2 pi, 3 pi, so on. The range is all the numbers not between -1 to 1, except for the endpoints. Its period is also 2 pi, just like sine is. It will never intercept the x-axis. Has vertical asymptotes, again, on all the intercepts. And it is also an odd function. If you rotate it 180 degrees, it will land on top of itself. Secant is still an even function. If you reflect it over the y-axis, it will land on top of itself. All right, so is there any questions about this? Let us look at an example. All right, last thing then, example. So let's say if the graph of y equals 2 cosecant of x plus pi over 4. To graph that by hand, we're going to graph y equals 2 sine of x plus pi over 4. As a review on how to do that, again, break this into its parts. Its a value is 2. That tells me that my amplitude, which was -1 to 1, is now between -2 to 2. And because it's positive, I am not reflecting this over the x-axis. Our b value is 1. And so that means the period is not changing at all. It's still 2 pi. Our c value is -pi over 4. So then this has a phase shift of c divided by b, which for our problem would be -pi over 4 over 1, which is -pi over 4. So that means we start at -pi over 4 when x equals -pi over 4 and add 2 pi later at 7 pi over 4. Right, 2 pi is the same as 8 pi over 4, and 8 pi over 4 minus 1 pi over 4 is 7 pi over 4. So if we graph that, halfway between these two would be, if you add them together, divide by 2, 6 pi would be 3 pi over 4. Our quarter ray point, again, add these two together and divide by 2. 2 pi over 4 divided by 2 is pi over 4. And our three-way point, 3/4 point would be 5 pi over 4. Or basically, if you look, your interval, again, take your period, 2 pi, and divide by 4, that you get pi over 2. So every pi over 2, or 2 pi over 4, right, is when you move to the next critical point. All right, remember sides pattern is intercept, maximum, intercept, minimum, intercept. So its function looks like this, or its graph looks like this. Wait. Oh, that's wrong. That's better. I'm like, that looks weird. There we go. And then to graph cosecant, this is what I was talking about. It's just like 15 seconds of extra work. Every intercept, we're going to put dotted lines through. These are our asymptotes. And every max or min, we draw a U. That should touch. Let's try that again. There you go. That's all it takes to draw the cosecant. And again, ultimately at the end of the day, if you're like, I don't know if I could do that by hand, you could always go to Desmos, graphing calculator, and graph to confirm that you really did do it right. So we really did have max and midpoints at pi over 4, 2 and 5 pi over 4, -2. All righty. Notice that they don't have the asymptotes in here, but if you, again, draw them in yourself, you could check and make sure.